All right, so these rules that we're going to talk about, these differentiation rules, the rules of taking a derivative, these all come from our limit definition of a derivative. So here's rule number one. If f of x is equal to c, then, now before I fill in f prime, I want to take a look at what this looks like. F of x equals c. C is a constant. So whatever your favorite number is, Nick, what's your favorite number? 32. 32, okay. So in the case where Nick's favorite number is 32, the graph of f of x equals 32 looks like a horizontal line at a y value of 32. Now, what is the slope of this horizontal line?
0.
So that tells us that the derivative of f of x equals 32 is 0. And in fact, that's true for any constant. Any horizontal line, its derivative will be 0. So if f of x equals c, then f prime of x is equal to 0. Now I mentioned right before I wrote down that rule that every single derivative rule comes from our limit definition of a derivative. So I'd like to check this one here. And so my check is, we're going to say f of x is equal to c. So f prime of x will be the limit as h goes to 0 of f of x plus h minus f of x all over h. And so we'll fill in f of x plus h. So everywhere that I see an x in my original function, I'm going to replace that with an x plus h. There is no x in our original function, so I don't have to do any replacing. So f of x plus h is c. And f of x itself is also c. So we have c minus c over h. So our numerator looks like 0. So we've got the limit as h goes to 0 of 0 over h. And 0 divided by anything is 0. So we've got the limit as h goes to 0 of 0. And the limit of a constant is the constant itself. So what we've just done is proven that the derivative of a constant is equal to 0, using the limit definition of the derivative. All right, any questions about that one? All right, so that's differentiation rule number 1. Number 2, and by the way, our goal today, we've been spending quite a bit of time talking about what is the meaning of a derivative. Derivative talks about slope of a function, and we've been kind of trying to understand that conceptual idea. Not so much concept going on today. Okay? Today is all about learning some tools that we're going to want to practice a ton of in order to become really good at these tools and these rules. All right, so rule number 2. If f of x is equal to x, then we want to know what our derivative will look like. So what does the graph of f of x equal to x look like? Yeah, it's a diagonal line, and it has a slope of 1. And that's true anywhere on the line. And so if f of x is equal to x, then the derivative is equal to 1, because the slope of our line f of x equals 1, or f of x equals x is 1. All right. We're going to check this one using our limit definition as well. We're not going to do this for all the rules, but we are for a few of them. All right, so we'll box this guy off. And so our proof that this statement is true is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Our original function is f of x equals x, so everywhere I see an x in the original one, I'm going to replace that with an x plus h. So we've got the limit as h goes to 0 of x plus h minus f of x, which is x, all over h. All right, so we'd like to clean this up. What can we do? Yeah, we can cancel the x's. We have x minus x, and so that leaves us with the limit as h goes to 0 of h over h. That simplifies even more. Gives us 1. So we have the limit as h goes to 0 of 1, which is 1. So if f of x is equal to x, f prime is 1. All right, rule number 3. Rule number 3 has an actual name to it. This is the power rule. I'm going to write down the power rule, and then we're going to talk about how we use it. So the power rule says if f of x is equal to x raised to the n, where n is a real number. So if f of x is equal to x to the n, then f prime of x is equal to, I'm going to say this out loud and then I'll write it down. F prime of x, what we're going to do is we're going to bring that n down in front and subtract 1 from the power. So our derivative is n times x to the n minus 1. All right, so for example, if I have f of x is equal to x to the 5th, then our derivative function, I'm going to bring that 5 down in front, and x is now raised to 1 less power, so we have 5x raised to the 4th. And as a second example, if I have y is equal to x to the 7/3, then my derivative, one way I can write my derivative of y is I can just call it y prime. And so even though this is a fraction, it's still a real number, so I can still bring that down in front. So I have 7/3 x, and 7/3 minus 1, well, I've got to make sure that I have common denominators. So my new power is 4/3. All right, any questions about the power rule? Now, this one becomes a little bit trickier to prove because suddenly we have an n up here which is not just a solid number. I mean, that n can be any real number that we want it to be. So maybe it might be a good idea to prove this for a particular value of n. Let's go with n equal 10. So for n equal to 10, our original function is f of x is equal to x to the 10th. And so our derivative will be 10x to the 9th. Now, to show that this is true, our proof will start out with f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And so now we'll plug in everywhere I see an x in my original function, I'm going to replace that with an x plus h. So I've got the limit as h goes to 0 of x plus h raised to the 10th minus f of x, which is x to the 10th, all divided by h. All right. Our next job is to expand out x plus h raised to the 10th. So that's x plus h times x plus h times x plus h, 3 times x plus h 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 times x plus h. All right, so this is going to be a really long expansion, and I don't really want to do this in class. So this is a little intimidating, not overly intimidating. But what I'd like to do is I'd like to leave that for you as an optional extra credit. So if you would like